In this video, I will show you the gory details of the neutron diffusion equation. This is a step-by-step walkthrough on how to solve it to determine the critical mass of an atomic bomb. I guess this is obvious, but there will be math. It is not terribly complicated math, but requires that you feel comfortable with some basic calculus. You are more than welcome to grab pen and paper and follow along. If you have any questions, just post them in the comments below. Let us first establish the problem that we want to describe and solve. We have an unknown mass of pure uranium-235. We will define its shape later. And we initiate the reaction with a burst of neutrons that will freely wander inside the uranium. By the way, this is what makes neutrons so special. They have no electric charge, so they move with little resistance between the atoms inside materials. On average, after a few centimeters, each fast neutron will encounter a uranium nucleus, which can fission or elastically scatter the neutron. The first reaction will release energy and produce more neutrons, feeding the chain reaction. In the second reaction, the neutrons simply bounce, barely losing energy so they can go and fission another nucleus. We want to determine the neutron density inside the material. This is the function n of x and t inside the uranium, where x represents the three spatial coordinates and t is a time measure from the moment the first neutrons are released. If the number of neutrons remains constant, then the density changes in time following the so-called continuity equation. The first term on the left is the rate at which the density changes with time. In the second term, J represents the flow of neutrons through a small volume. This is usually called a current. If the name suggests the idea of an electric current or the motion of a fluid, it is because the mathematics of electric currents and fluids is very similar. If you check, for example, the Feynman Lectures, Volume 2, Chapter 12, you will find a collection of physical systems described by equations similar to those used in electromagnetism. And indeed, Section 4 is about neutrons diffusing inside a material. Contrary to electric and fluid currents, in our case some neutrons disappear, consumed by fission, and new neutrons are created. The right-hand side of this equation will not be zero, but will come with two extra terms. One for the rate at which new neutrons are created, let's call them a source, S+, and another term for each neutron that is consumed by each fission. Let's call it a sink, S-. We will determine these two terms in a minute. Neutrons created in the volume will increase the density and will begin moving to regions of lower density. This is a general behavior known as Fick's law, and it is crucial for a large number of physical, chemical, and even biological systems. Mathematically, Fick's law is written as J equals minus D times the gradient of n, which can be understood as the flow of neutrons is in the direction of less density. The proportionality factor D is called the diffusion constant, and it measures how eager the neutrons are to diffuse around. And it can be written as 1/3 of the average speed of the neutrons times the transport mean-free path. As a reminder, the mean-free path measures the average distance between one reaction and the next. Replacing the current from Fick's law into our continuity equation, we get the following. Here we get a divergence acting on a gradient. And a quick search will show you that the divergence of a gradient is equal to the Laplacian of the function. We will see the explicit form of this Laplacian operator when we solve the equation. Rearranging terms, we get that the change in neutron density as a function of time is just given by the neutrons gained minus the neutrons lost. The source term, S+, is the rate at which the neutron density n changes with time due to the creation of secondary neutrons from each fission reaction. We can write it as the average number of neutrons created by fission, which we denote by the Greek letter nu, times the density n divided by the average time between fissions, which is denoted by the Greek letter tau. Similarly, the sink term, S-, is given by the rate at which the neutron density n changes with time due to the elimination of each neutron that produces the fission. So we can write it as 1 times the density n divided by tau. Putting all these terms together and replacing the value of the diffusion constant, we finally find the mighty neutron diffusion equation that I have shown you in several videos. Note that because the average neutron speed is the fission mean-free path, lambda f, divided by the average time between fissions tau, this equation can be written in different ways, but they're all equivalent. From here, I will use the expression shown in the third line. I mentioned earlier something called the transport mean-free path. This is just a name to indicate that this mean-free path does not refer uniquely to fission or elastic scattering, but in fact is a combination of both. So keep in mind that we have two mean-free paths, one for fission, which is written in terms of the fission cross-section, and a transport mean-free path written in terms of the transport cross-section, which is simply the cross-section of fission plus the cross-section of elastic scattering. And now that we have our equation, we solve it. What we have in front of us is called a partial differential equation. Notice that n, the Neutron density, depends on position, the three spatial coordinates, and time. There are different methods for solving this type of equations, but I will use one of the simplest ones, which is called separation of variables. In this method, we make the assumption that the function that we are looking for, the density n, can be written as the product of two independent functions. One is only a function of the spatial coordinates, x, and the other is only a function of time. And I have called these functions f and g. Now we replace this into the original function, and we notice that on the left, the time derivative only acts on g, because f is independent of time. Similarly, on the right-hand side, the Laplacian operator, which only involves spatial coordinates, only acts on the function f, because g is only a function of time. The next step is we divide by f times g, and what we get is, on the left-hand side, only a function of t. There is no spatial dependence on the left-hand side. Similarly, on the right-hand side, we have a bunch of constants and quantities involving the spatial part. There is no time dependence on the right-hand side. And here comes the magic of separation of variables. If the left-hand side of the equation depends only on time, and the right-hand side of the equation only depends on space, the only way this equation can be satisfied for any position and any time is that both are equal to a constant. This constant, that I call k, is called the separation constant. I could just leave it as k, but I will do one more trick. If you look at the left-hand side of the equation, you will see that everything has units of 1 divided by time. That means that k also has unit of 1 divided by time. And just for simplicity, and in fact it's going to be a very convenient definition, instead of k, I will use nu prime divided by tau. Nu prime is still completely unknown, we will need to find it later, and tau is again the time between fissions. The reason I do this is that now my separation constant, nu prime, has no units. That's all. It's only because it's convenient. We move from a complicated equation, partial differential equation, into two simple ordinary differential equations. The price that we have to pay is that now we need to solve two equations instead of one, but they are not necessarily hard to solve. Let's start with the time evolution. Take the equation that we derive for g. This is probably one of the first differential equations that you learn how to solve because it's the easiest one. The solution is just an exponential in time. A is called an integration constant. This is a number that we still don't know and we will need to figure out later using the boundary conditions. If we analyze very quickly our solution, we find that g changes exponentially with time. Whether this is an exponential growth or an exponential decay will directly depend on the sign of nu prime. This makes nu prime an extremely important quantity, and we will see that later. In fact, nu prime will be crucial for determining the critical mass. So once again, notice that if nu prime is positive, we have an exponential growth, and this will describe a supercritical reaction. If nu is negative, we have an exponential decay, and in this case, we will have what is called a subcritical reaction. And for this reason, nu prime is usually called a criticality factor. Now we move to the other function f. I just copied the equation that we derived earlier. Notice that tau goes away. And just for simplicity, I have collected all the constants in front of f and rename it kappa square. This is just because I don't want to write all that expression many times. So rewriting it, we get this quite simply looking differential equation for f. We need to know what this Laplacian operator is. And this is a very important step because the Laplacian operator depends on which coordinate system you use. So here is the step when we need to choose a geometry for our uranium core. And we will pick the simplest possible case, which is a sphere. And not only that, I will make the sphere to be homogeneous. That means that if I rotate this sphere, nothing will change. This is called spherical symmetry, and in writing the function f of x, that means that my function f only depends on r. And by doing this, the Laplacian operator simplifies a lot, because in principle it comes with 3 terms, but the angular parts will just disappear. They're just 0. And we get this expression. When you have the derivative of a product, that would lead you to 2 terms, and that will make the equation too complicated. But there's a trick. We can introduce an auxiliary function. If you replace f by u divided by r and expand all the terms for the Laplacian acting on f, you will find that you get a single term given by 1 over r times the second derivative of u respect to r. And now we replace this in our original equation, and what you get is a very simple looking equation. Now, this equation is known to every physicist. I think it's the first equation that we learn how to solve, even without taking any course on differential equations. This is the first equation that we learn how to solve. This is called harmonic motion, and the solution is the sum of a sine and cosine functions. And now that we have u, we find f by simply dividing by r. And again, we have 2 integration constants called b and c. We don't know what they are yet, and they have to be defined using the boundary conditions. So now we can write the full solution. Density is a function of r and t, and is given by the product of the 2 solutions that we found, g and f. In total, we have 4 unknowns, a, b, c, and nu prime. Now we impose the boundary conditions. What we have written on the top is a function that mathematically solves the Neutron diffusion equation. Now we need to restrict to only those solutions that make physical sense. The first boundary condition is that the Neutron density cannot be infinite at the center. If we take the limit of r going to 0 of the cosine term, we find that it will diverge. If you ever study limits and you thought that you would never use them, well, they come up every time you want to solve differential equations. If you take the limit of r going to 0 of a cosine of kappa times r, is close to 1 for small r, so this term will blow up, goes to infinity. The only way that we can guarantee that the Neutron density is finite at the center is by setting b equals 0. In this way, we completely eliminate this term from our solution. If we apply the same limit to the other term, we find that everything is fine. So the limit of r going to 0 of sine kappa r is not 0, but kappa r. The 2 r's cancel out and we just get kappa times the constant c. That means that c is not 0. The second boundary condition that we will impose is that the initial neutron density at the center will be given by n0. In other words, we will just call n0 the initial burst of neutrons that will start the reaction. We take our general solution, we evaluate it in the limit of r and t going to 0, and that has to be equal to this constant n0. If we take the limit of our general function, we get ac times kappa, and that means that a times c must be n0 divided by kappa. Notice that we don't know anything about c or a, but we know that the product, which is what we need in our solution, is equal to n0 divided by kappa. And with this, we have eliminated 3 of our 4 integration constants. What we get is a solution that depends on r, t, the time measured from the initial burst of neutrons, and nu prime, which is a quantity that we still don't know. For this, we set our third boundary condition. We're going to impose that no neutrons are escaping from the sphere. We want the density to be exactly 0 at the boundary. This boundary condition is not completely true, and this is why I'm calling this elementary solution. We will see in a minute that there is a more advanced solution. But for now, let's impose that at the edge of the sphere, no neutrons will escape. We evaluate our function at r equal the radius of the sphere. All the terms outside the parentheses are positive numbers, so we can get rid of them. Similarly, the denominator inside the parentheses is a positive number, so the only way that this equation can be satisfied is that the sine of kappa times r is equal to 0. And if you remember from trigonometry, the simplest solution for sine of something equals 0 is that something, in this case kappa times r, is equal to pi. And from here we find that kappa must be pi divided by r. But notice something that happens here. Now we have 2 ways of writing kappa. We have the original definition of kappa in the form of kappa square, and now we know that kappa is also pi divided by r. If I take the square of this kappa that we just found, it must be equal to the original definition of kappa. And from there, what we find is an equation that only depends on nu prime, which is the quantity we want to find. So here you just need to manipulate this expression a little bit, and after some algebra you will find that nu prime can be written in terms of nu, the transport mean free path, the fission mean free path, and the radius of the sphere. In other words, we have finally found our last integration constant. This is the final complete solution. Still, I call it elementary because of the boundary condition that we use, that no neutrons will escape from the sphere, but notice that we know all the quantities. So if you're with me at this point, you can finally say, we have solved the neutron diffusion equation. And with this final solution, we are ready to calculate the critical mass. Before doing that, I just wanted to announce that I have launched a Ko-fi account. So if you feel that you could support the channel, that will be highly appreciated. If not, that's totally fine, but any donation will be highly appreciated. Please head to ko-fi.com/jk0 and pick the donation that is okay for you. Thank you so much in advance. And now, let's go back to the critical mass. Since I now want to make some plots, I have listed on the top right the measure values for tau, nu, and the two mean free paths. So let's explore our solution. In this plot, I have the coordinate r measured in units of the radius. That means that the point 1 is the surface of our sphere, and in the vertical axis, I put the density in some arbitrary units. If we assume that nu prime is negative, let's see what happens. This yellow line represents n0. This is the initial burst of neutrons that we have at t equals 0. And the curve shows how they will distribute inside the uranium. They are mostly concentrated at the center, and they decay to 0 exactly at the surface. Now we let time evolve, and we see that the densities start dropping, and it starts going to 0. This is why this kind of solution is called a subcritical reaction. Start with the burst of neutrons, there will be some multiplication, some fission, but as time evolves, it will very quickly die off. Let's now use a positive nu prime. We start with exactly the same profile that represents the initial burst of neutrons, and we see that as time evolves, the neutron density quickly starts going up. I let this evolve only a few nanoseconds, just to give you an idea, and you can see that this will very quickly start blowing up. Notice that every time, most of the neutrons are close to the center, and they drop to 0 at the surface. But still, they will move away from the center, and they will occupy most of the volume inside the uranium, and the number of neutrons will grow exponentially, and with this, more and more fission. This is a supercritical chain reaction. What we can conclude from here is related to what we discussed earlier about the meaning of nu prime. Negative nu prime is a subcritical reaction, positive nu prime is a supercritical reaction. So let's have a look at this function on the top right and see how the sign of nu prime depends on the radius of the uranium sphere. The plot clearly shows that for a radius below 11 centimeters or so, nu prime is always negative. That means if your mass is too small, so that the sphere has less than 11 centimeters, you will not have a chain reaction. If you now put more mass together, so you get a sphere with a radius larger than 11 centimeters, nu prime is positive. That means that you will have a supercritical chain reaction. So here we can evaluate and find an expression, a mathematical expression for criticality. We set the criticality condition to be nu prime equal to 0. And from the expression above, we can simply solve for the radius. And that gives us the critical radius that we usually denote RC. It is given by a combination of pi, which is a constant, the mean free path for fission and for transport, and the average number of secondary neutrons produced by the reaction. There is another way that I would like to express this relation, and that is by reminding you that the mean free path is in general given in terms of the atomic mass number, A, the density of the material, Avogadro's number, and the relevant cross-section. Replacing the two lambdas in this expression in terms of their corresponding cross-sections, we find this more complicated looking expression, but we can isolate the dependence on the density of the material. And this is important because the critical mass is given by the density times the volume. Putting all together, we finally find a very general expression for the critical mass that only depends on a bunch of constants that are unique for the material, in this case uranium, and the density. I stress this because in previous videos I have told you that the density is very important because if you increase the density, like in an implosion bomb, you can reduce the critical mass. If we leave implosion aside for a moment and we only focus on normal conditions, and if you plug all the numbers you can find that the critical radius for uranium-235 is 11 centimeters, and that leads to a critical mass of 106 kilograms. But again, I cannot stress enough the importance of this expression. We have a mathematical formula for the critical mass in terms of a bunch of constants that depend on the material and its density. Before I wrap it up, I would like to mention something that is very important. I told you earlier that the solution that we found for the Neutron diffusion equation was called elementary. And elementary meant that we were forcing the number of neutrons to be zero at the surface of the sphere. In other words, we were trying to prevent any neutrons from escaping. But this condition can be a little bit too strict, because we might let some neutrons escape, that's fine, as long as we can compensate the neutrons that we are losing through the surface that are escaping by new neutrons that are being created by fission, we'll still be fine. And in fact, it will dramatically reduce the critical mass. The reason this is called the advanced solution is that we're going to use an expression for the boundary condition, so for the third boundary condition, that is a little bit more complicated to prove. I will not do that here, but it's given in terms of the gradient of the density evaluated at the surface. So here, in case you're motivated, there is a nice exercise. You can use the expression that we found, the general solution that we found here, take the derivative and evaluate it at the surface, and what you will find is this equation. This is called a transcendental equation. That means cannot be solved analytically. The only way to solve it is using numerical methods. But there's also a nice way to visualize this kind of equation. What you do is you plot the left-hand side and the right-hand side, and you look for the point where they cross. In this case, the left-hand side is just a straight line in terms of r, which again is the radius of the sphere. For the right-hand side, you need to know the value of kappa, which again we have on the top right, and we set nu prime equals 0 because we're looking for the critical condition. And we will find that these two curves will cross each other for a radius close to 8.4 centimeters. And with this radius, you can calculate the volume, multiply by the density, and find that the critical mass is 46 kilograms. And here you can see the importance of this advanced solution. The fact that we can allow some neutrons to escape because we are producing so many new neutrons inside the material by fission, by this exponential growth, we have been able to reduce the critical mass to less than half of the elementary solution. So here is the critical radius and the critical mass for uranium-235. So far, I have assumed the bomb core to be uranium-235, but if we use the parameters for plutonium-239, we can get the corresponding critical radius and critical mass. If you want to test what you have learned, here are the necessary parameters. I suspect that nobody is expecting a homework assignment from a YouTube video, but give it a try. I got the values shown here using the elementary and the advanced diffusion theory for a bomb with the plutonium-239 core. I should mention that there are several implicit assumptions made in all this calculation. However, all the results found here agree very well with experimental values, which shows that despite some limitations of the formalism, the results are a very good approximation of reality. Another comment is that I have not included neutron reflectors, which can help to reduce the critical mass even more. What we have calculated here is the so-called critical mass of a bare sphere. So there you have it. We have derived and solved the neutron diffusion equation and calculated the critical mass for a spherical bomb. This is exactly what Rudolf Peierls and Otto Fritsch did in 1940. If you feel motivated, you might want to try other geometries. For instance, Little Boy, the first uranium bomb, had a cylindrical core. Just write the Laplacian operator in the appropriate coordinates and solve it following the steps shown in the video. In fact, here is another exercise in case you feel inspired. Imagine that you have a cube of uranium of side A, and you can try to find the critical value of this side. Once you have the critical value, you can determine the critical mass. And the key point here is compare that to the result from the spherical bomb. This exercise will show you that the shape of the core is very important for determining the critical mass. So I encourage you, give it a try. Let me know in the comments what you find, or if you get stuck, I'll be happy to help you out. I hope you found this video of interest. I warned you that it would be math heavy, but I really wanted to document this historic result and show you all the steps to follow along and reproduce them. This is one of my personal favorite physics calculations, and if you watch the video about Heisenberg and the German bomb, you understand the importance of this result. The other day, after I reproduced this calculation, I could only stare at my notes and think how this calculation was once the most heavily guarded military secret.